Welcome to Unit 10, Lesson 2, Sum, Difference, and Double Angle Identities. On your page, you have something called the golden equations, and they are also on your formula sheet. They're all shown there for you and simplified. So we have three different sets of identities that can help us to solve problems, and what I want to encourage you to do is use your formula sheet and compare the question you're given to the identities that you're provided. And it will be very easy to solve these problems once you just recognize the spots of A and B in all these identities. The location and what the identity looks like will tell you how to solve the problem. So we have three sum identities. They're defined here: sine A plus B, cos A plus B, and tan A plus B. And they break down into these components. We have three angle difference identities, and they're listed there as well for sine, cos, and tangent. And then we have something called the double angle identities. Sine 2a is equal to 2 sine A cos 2a is equal to cos squared A minus sine squared A, and then tan 2a is equal to 2 tan A over 1 minus tan squared A. Now, some mathematician at some point in time has done all the proof to make sure that these are true for you. You kind of just need to take them as is and then see what are the locations of A and B to help you solve the problems that you're given. Now, these questions can either be done in degrees or radians. Whatever you're provided with, just go with that and solve it that way. If you try and switch back and forth between the two, you're going to get confused and make mistakes. So keep it simple. Don't overcomplicate it. Now, the first question, we have sine 48 cos 18 minus cos 48 sine 18. Notice that I've gone through and just labeled to signal to myself where A and B lie. So AB, AB. Now, if you compare this question that you're given up to the angle difference identities at the top, you'll see that this is equivalent to sine A minus B. So once you have this statement, you just fill in the brackets: sine, put the value of A, put the value of B, and subtract them. This whole thing simplifies down to sine of 30, which on your unit circle is 1/2, or the y coordinate. The same thing in the cosine question provided here. You can just look through the example and do it yourself. I just wanted to talk briefly about this one down here, the tan 10 degree answer. This is an okay answer if it's one of the questions that you're not able to use your calculator for. You can just leave it like that. Some questions are just not able to be simplified further without the use of a calculator. And of course, 10 degrees is not one of the values on our unit circle directly. So that's a perfectly fine answer. Question 4 is an example of doing it using radians instead. So nothing changes. You just look at the pattern you're given: cos, cos plus sine, sine. That relates to the cosine angle difference formula, cos A minus B. And then you just plug in those values: 7 pi over 12 minus 5 pi over 12. A note here: make sure that you're using common denominators if you're dealing in fractions. Here it is, but it may not be in other questions. So simplifying it down further: cos 2 pi over 12, cos pi over 6, and then straight to your unit circle for the final answer of root 3 over 2. On the back, there's an additional example in number 5, but again, just following the formulas. In part B, simplify expressions using double angle identities and determine exact values. So in this section, we're using our double angle identities to solve these problems. In question 6, I made an error. I forgot to insert the squared. So while this question is solvable, it's not the one that we're trying to solve. Just please rewrite it as cos squared 2 pi over 3 minus sine squared 2 pi over 3. And once you have that, here's your A. It's just 2 times A. So cos of 2 times 2 pi over 3, which is equal to the cosine of 4 pi over 3, which from your unit circle is negative 1/2. The rest of the examples are really similar. Here we have 2 sine pi over 12, cos pi over 12. So again, it's just a double angle identity. You're just multiplying A times 2 and then solving. So sine of pi over 6, which is your y coordinate, and it equals to positive 1/2. In the bottom here, you have two examples that are not similar to the golden equations that were given on the front, but they are on your formula sheet if you look for them in that format. So I just put a little note which one it corresponds to. Cos 2a is equal to 1 minus 2 sine squared a. So if we have it listed in this format, which we do, you just solve for cos 2a, cos of 2 times 30, cos of 60, and 1/2. And then the same thing over here, cos 2a is equal to 2 cos squared a minus 1, also on your formula sheet. And here the cosine of 180 is -1. In part C, develop expressions using sum and difference identities and determine exact values. You're not always going to be given a value that corresponds perfectly to your unit circle, but we can create that angle that we're provided by using the angles on the unit circle that we do know. So for example, sine pi over 12, if you look at your unit circle, it's not broken into 12s, although it could be, but it's just not one of the common ones. Here we're going to use the difference identity for sine for two special angles. For example, because pi over 12 is equal to 3 pi over 12 minus 2 pi over 12. These two fractions simplify to pi over 4 minus pi over 6. So in this situation, you're not worrying about a common denominator. What you need to do is create a situation that creates your angle that you're given and then solve using the identities that we just learned. So for example, sine pi over 12 is equal to sine of pi over 4 minus pi over 6. And then once you have this, here's your A, here's your B. You're going to use the corresponding identity, which is sine A minus B, and then just plug in the values from your unit circle and solve for it. We get root 6 minus root 2 over 4. They share a common denominator when you crunch the numbers down. So if you're given an angle that doesn't fall on your unit circle, you can build it using components that you already know. The second example is tan 105 degrees, so again, not on the unit circle. I've included two different methods to solve this problem. Both are valid. So method 1, use the difference identity for tangent. So you can rewrite tan 105 as a difference of special angles. So we know 135 and we know 30, or equivalent to 3 pi over 4 and pi over 6. Now, once you have this statement, tan A minus B, you just go to your formula sheet, find that identity, which is right here, and then plug in the values and solve. So it gets a little crazy in the solving, but if you just go step by step, I think it will be simple. You're just plugging in the values for tan of 135 and tan 30 all throughout the equation wherever they fit in. So you come down to the bottom here, root 3 plus 1 over 1 minus root 3. There's a question for extension here, how could you rationalize the denominator? So of course you would just multiply top and bottom by the 1 minus root 3 to get rid of that radicand in the denominator. But if you leave it like this, that's also perfectly fine. Proving that there's more than one way to solve a problem, you can also use a quotient identity. Both of these solutions are valid, so whichever one you selected would be perfectly acceptable. So we know that tan 105 is equal to sine 105 over cos 105. And then 105 degrees, it just gets broken down into A, 60 degrees, and B, 45 degrees. Very important that A and B are in the same place in these two identities, or else you will not get the right answer. So once you've done that, you just go back to your formula sheet and look for your sum identities, which is sine and cos right there, and then write them out and fill in the values. You may find it beneficial to include a step right here, which would be to write out sine A cos B, cos A sine B, etc. To just make sure you're using your formula as a map to tell you where to put it. I know it takes a little bit of extra work, but it's really beneficial as a mathematician in the long run if you utilize your formulas in that way, because if you have your map where to go, then there's no way you can do it wrong. So I encourage you to include that extra step there if you're not sure where to go. Just write it out and guide yourself through it. Anyway, at the bottom, it gets down to root 6 plus root 2 over 2 minus root 6. You could simplify this further, of course, by pulling out the root 2 out of everything. So divide all terms by root 2. And you would get the same answer as above, root 3 plus 1 over 1 minus root 3. So both solutions valid. Pick the one you like and the one that you're comfortable with and go with that. There's 2 additional examples here in number 11. You can just pause the video and copy down the solution. In B, I just wanted to point out that tan of 11 pi over 12 is in quadrant 2. So what you're going to want to do is find your reference angle, which is, of course, pi over 12. But because it's in quadrant 2, it has to be negative. So you're going to pop that negative value at the front of your tangent. Just to signal yourself what quadrant you're actually working in to make sure at the end you get the right positive or negative in the answer. So just be conscious of that as you're looking at the locations of your angles, specifically when you're working in radians. D is a lot of work. So use the exact values of trigonometric functions to find the value of a trig identity. In the question, you are given sine A. Now, just keep in mind here, they're telling you sine A. This is not the value of A like we've seen in previous questions. This is sine of A. So when you go down to your formula, you're just plugging the value straight in. You don't have to worry about doing any extra work. So with that, we know sine A is 7 over 25. I just want to bring you back to your Pythagorean theorem if you forget how to do it. If we know that sine is opposite over hypotenuse, and we just draw this little triangle here, opposite over hypotenuse, you can just solve for that third side. C squared minus A squared gives you B squared, and you'll get 24. The same thing for this one, cosine B. The 9 is the adjacent side to whichever angle you've selected, and the 41 is the hypotenuse, so we get this triangle 9, 40, 41. I think this is a really beneficial thing to draw out for this question so that you can kind of visualize how am I building my ratios. I just included this in here so that later on we don't need to figure it out. The tangent of A is 7 over 24 and the tan of B is 40 over 9. Now, since we know these values for sine, cos, and tangent already, when we're given these questions, we can just go ahead and solve it using multiplication, addition, subtraction, division. In sine A plus B, you're just taking the values from the question, 7 over 25 plus 9 over 41. Notice that it's creating a nice common denominator for you. If you're able to simplify it further, please do reduce your fractions, but if it's not possible, then just leave it as is. So you get down to 63 over 1025 plus 960 over 1025, and those combine to give you 1023 over 1025. Cos A plus B is very similar. You're just plugging in the values that you've found, and you should come out to negative 64 over 1025. In C, tan A minus B. Now you need to remember that the tangent is a ratio. So in this question, it's a little bit simpler because we've already found that value based on our triangle, 7 over 24 and 40 over 9. So here we can just plug the values in, but don't forget that tangent is sine over cosine. Now, what you're going to do, just plug in those values and solve, and you get up to here. You get negative 897 over 216 divided by 496 over 216. Just take this, flip it, and multiply through to cancel out the 216s. You'll get negative 897 over 496. It's about negative 1.8, but you can just leave it as a fraction here. In D, I guess D would be a bit of a challenge question because you're not provided with the formula for cotan of A minus B. It's not simply just flipping the tan A minus B formula over, unfortunately. So I've just provided you with the proof here and what that actually equals. You can also just go on Google and search up what is the proof of cotan A minus B, or what is the identity that represents it, and it'll give you a big long-winded thing. But for this question solely, I don't think it'll come up again because most of the questions deal specifically in sine, cosine, and tangent. But this is what it is. Cotan A, cotan B plus 1 divided by cotan A minus cotan B. Now, it's cotangent, okay? So what you need to do is take your tangent values from above. Tan A is 7 over 24. You need to flip that, 24 over 7. And then this one needs to get flipped as well, 9 over 40. Once you've done that, it's just simple and straightforward. You're just going to go through and solve for the value of the fraction. Once you simplify it down, you're getting that common denominator of 280. Notice here that I changed the 1 to 280 over 280 just for simplicity's sake. So 216 plus 280 gives you 496, and then 964 minus 63 gives you 901. Flip and cancel the 280s, and you should end up with 496 over 901. There are no practice questions associated with this lesson, and you can just prepare for class tomorrow.